All right, welcome everybody. This is Fred Schenkelberg, and today we're going to talk about a massive topic of reliability testing. And I'm really going to try to focus on just a few of the essential pieces in order to help you get the most out of the testing that you do, and then make sure that it actually is useful and beneficial for your organization. And we'll get into a good part of that detail here in a moment. And apparently this is a pretty high interest topic. Excuse me, I got a little frog in my throat. We got a good turnout today, so I appreciate that. And feel free to jump in with questions or enter stuff into the chat window. I'll be looking for that on occasion, plus a handful of prompts for you to get involved with the presentation. Now, I remember years ago, I was working at Hewlett-Packard, and we had a test engineer that she worked on creating the bed of nails type circuit board testing. And it was a functional test for inline with the production of the circuit boards. And those were really expensive systems, and they worked very fast, and they typically covered 90+% of the functionality and components on the board. So they did things like open and shorts and functional tests and voltage readings at particular insertion points and so on. They did all kinds of sophisticated testing. Now, in her mind, when I talked about testing, she always thought I was talking about this electronic circuit board functional testing type stuff. And of course I wasn't. There is so many different ways we evaluate, examine, explore, and destroy, in many cases, our products, electrical, mechanical, and software. And we do a lot of testing, and there's lots and lots of different material out there, and research and ideas and names and all kinds of stuff about testing. And so we're going to talk about this, some of the details that are related to what I would consider reliability testing, but I'm certainly not going to cover all of them. Now, sometimes we do life testing. I'm not really sure what that is. Generally, welcome David and William and Miraja. I'm not sure I'm pronouncing that, Nasir, and a bunch of others. Thanks all for joining in and saying hi. Good mix of folks. But let me get back to life testing. Now, I've heard that in many different organizations, and I've heard it associated with robustness, with durability, with will it last long enough? Will it last some period of time? Confirming information going on the data sheet related to the longevity of a product. Yet there are so many ways to evaluate and estimate the life of a design. So this is one of those terms I see very, very often, yet I have never nailed down a good detailed description of what a life test is. Now, we'll touch on this again as we go. And then one of the things I want to highlight here, and I'll bring it up again and again, is we do testing and we often run into failures. Now, sometimes the failures are in our test design itself. I remember the first accelerated test I did is my ovens had such horrible temperature control that it was probably 30 to 40 degrees C variation across the chamber. And so some parts got really, really hot and some parts didn't really get all that much of a temperature increase. And of course that influenced what failed and how often they failed. And realizing that partway through the test, what was to be a 6-month test, really set me back quite a bit. Now, some failures are deliberate, like halt testing. We force our design to fail. And other failures are unexpected. We actually learn something at that point. But failures are part and parcel to testing, to evaluating and stressing our products. So it's not something that's a bad thing. It just is what it is, and we need to know how to plan for it or deal with it. And so shouldn't be any surprises there. And I'm sure many of you have heard me talk about failures as being really useful in so many different ways, whether or not it's in testing, that we can benefit so much from having failures actually occur that, well, in testing, we should, in my opinion, try to get failures. It's always a good thing. And so let's back up a little bit. Let me ask you, use the chat window if you'd like. What's the purpose of reliability testing? What is this for you? Why do we do reliability testing? Don't be shy. There we go. There's a few people chiming in. All right, I'm going to bring the survey back, and if you haven't filled this out yet, you can go ahead and click on the types of testing you do. A few more people are typing ideas in here of what's the purpose of testing. I'll summarize here in a moment. All right, before this rolls off my screen here, from ideas of product performance and to find weak links, to see what fails and how it fails, to discovery. Appreciate everybody using the word discovery. It's my addition to the lexicon of, or at least I hope it is that we're exploring how things work or don't work. And it's a process that I enjoy using quite often. End of life determination, really looking for, will this product last 10 years with some probability of success, and confirming our modeling and estimations and so on. Looking for, is our design useful? Does it work? Design margins, that's often a good one. We do a whole range of different types of testing to determine, will it work in all the different ways our customers use it. We'll certainly spend a little bit more time on that. Yeah, and as you gain confidence, does our design, does our product, does our assembly work? Sometimes that's an unknown, especially when it's new technology or first time we're working with a particular technology. And Gene, good point. It's risk management. We want to understand or reduce the amount of uncertainty we have with a particular product or design. Does it work in different circumstances, and does it work well? Those kinds of things. And looking at different levels of this. So lots and lots of different purposes, right? And that's all fine. What I'm not seeing, though, is one of them I think is critical. And I think it's underneath many of these different suggestions of what's the purpose of testing. So let's see. And it's still, yeah, we do a lot of testing all across the board. I think there's just a few people say, no, we don't. It might be that you don't do it or your organization doesn't do it. And that's fine. There are types of products and types of systems that have two options. One, it's just not economical to do testing, so you don't. It doesn't really provide any benefit. Or I always, with tongue-in-cheek here, call it the Microsoft method, where you create your product and you don't do any testing, but you hand it off to all your customers and let them evaluate it for you. Some organizations can get away with that, others don't. Now, to be fair to Microsoft, they do an immense amount of testing on all their products. I know that firsthand. And it's just that they make really complicated products that are used in all kinds of unusual ways. So I call it the Microsoft method. All right. Yeah, there's lots and lots and lots of purposes for the testing that we do. And that's not surprising, right? Part of it is to verify performance, and a good number of you mentioned that. So if we have a question in our design process of, does this work? Will it work in cold temperatures or in hot temperatures? Will it work in upstate New York, or will it work in Brazil? Will it work for an extended period of time? Will the battery life actually be the listed or expected battery lifetime, and so on? So we're performing testing and checking that the functionality is appropriate, is actual. It actually occurs. Now, some of these are pretty easy, right? But some products are really, really difficult to verify the performance. I can think of all kinds of examples of single-use products, and one of the functions is that it has a 2-year shelf life. Well, how do you accelerate shelf life? And it goes back into the details of failure mechanisms and how it behaves and how it's stored and all those details. And that can be actually rather complicated to verify a product survives a benign environment. And for some products, that's actually pretty harsh. Other products, it's no big deal. Think of a piece of unprotected metal that's a spare part for some system that is stored in a humid area. And rust is a failure mechanism. So we could model that, we could analyze it, we could test it in real life, we can accelerate it, all those things. But how about items that have a diffusion rate for oxygen that is at its maximum at ambient temperatures in normal conditions? So if you increase temperatures, I used to work on a product like that, it became less susceptible to oxidation. If you chilled it, it became less susceptible to oxidation. That can happen. So there isn't a lot of options of how to accelerate it. So it always varies, right? But many times we look at testing to check, does it work under the expected set of conditions? And that's fine. Another one is discover, and a good number of you mentioned this as a purpose, is one of the great benefits of finding failures is that we have something to work on. Engineers love failures. And if you've ever brought a test failure to your team and they understand the value of failures, it's hard to hold them back to go solve it. We do need to do failure analysis, right? We need to understand the underlying cause of the failure, right? But we need to actually hold engineers back. Now, many of you have heard me talk about Henry Petroski in his book Design Paradigms, and he has a number of books out about design practices and the historical development of design practices. And in a number of his books, he comments that designers inherently design away from failure. And so if there's uncertainty, they build more margin into it. If they understand the weaknesses of their product, they have a margin that they know how to build. They know where to avoid. They can oftentimes design out the issue or the problem. And so it's great. Now, bringing a failure to a design team 2 days before launch may upset your program manager, right? Yet, at the end of the day, it's often better to know how a product is likely to fail and what your risks are than not. And so I call it discovery process. It's not something you pass or fail, halt testing in particular. It's a way to understand the areas that need improvement or the areas of risk. Any of our tests, just turning on a prototype for the first time, for example, for an electrical or electrical mechanical device, if it doesn't turn on, that's a failure, right? Let's sort out why that happened, and let's, we got to get it working so we can get on with our development. Yet that's valuable information in many cases as to what happened there. Why did it not work? And so those are all good reasons to do testing. But here's the thing I think is most important and covers the full suite of all the type of testing we do, is we do testing so that we can make decisions, right? We don't do testing just because we've always done it. I hope that's not the reason you do testing. And I didn't see that in any of the comments for the purpose of it. You know, we've got this fancy new test equipment, let's go use it and make sure we use it all the time. I've actually run into an organization that did that. They bought a whole pile of Holt chambers, and they required every prototype to be evaluated that way, whether or not it made any sense or not. They wanted to keep those chambers fully occupied, which was silly. And they learned very, very little out of those out of the expense of running their tests. Yeah, so Hojat, you mentioning some experience that engineers do not like failures, bring them to failure, and yeah, and that's a good point. Is that does the test actually create meaningful failures, right? And now I can go break a product. There's no doubt that we can fracture or break products, and hit it with a big enough hammer, we're going to break it. And of course, that has no meaning or no useful value to the design team. Right, so there is some engineering that goes into creating tests. But if you bring an engineer a failure and you have the understanding of the root cause saying, hey, this is a diffusion problem, or this is a corrosion problem, or this is a contamination problem, or it's a lack of tolerancing and we're getting excessive wear, or those kinds of things. Couple that with the magnitude of that. I remember, let me see if I can find my pen here. So I had I'm going to build on your comment here, Hojat, a little bit. Let me see where my drawing tool is. Here we go. So I'm going to do a quick aside. So I had a product, and it had a battery compartment, and I won't get too fancy with it. And it had a little wire that came off the positive side, I think it was, and it went at a right angle, and then a right angle, and I'll do a dash line for into the circuit board, right? So it had a little via here that it inserted and was attached. And the idea was that the wire would go in this space between the battery compartment and the top of the circuit board. Well, there weren't any features on this wire to keep it in the right spacing. So what happened is we went to Holt and we vibrated it for a few minutes, and the product failed, and we opened it up. You could smell the melted plastic in burning fiberglass, which is usually not a good sign for an electronic product. But what happened is this wire, the way it was built, touched the top of the circuit board. And on top of the circuit board, I'm going to draw a little aerial view looking down on the board, is there was a trace on that board, and there was the wire just happened to line up right on top of it. And so, of course, it was the opposite polarity. This was a ground trace, and this was the opposite polarity on this lead wire. And of course, with a little bit of vibration, it wore through the coating over that piece of copper on the circuit board and created a dead short, hence the problem. Now, I didn't anticipate this. The designers didn't anticipate this. Yet it took one photo and it went back to the mechanical engineers to solve this problem, to redesign this connection such that it wouldn't rub on the circuit board. It added some cost, but we also knew that this failure would likely affect the majority of all the products because the inability to control how this wire was inserted. And we knew that the circuit board could move. With vibration, it also moved in the z-axis. So even if it wasn't initially touching, it was going to bump into it pretty often, and eventually it would wear through. And that would be a problem. And so he said, here's a failure. It creates a non-repairable situation. It has this burning smell, which is not good marketing for a handheld product. It wasn't enough energy to catch it on fire, but it wasn't a pleasant smell. And it was likely to affect a half or more of the products in use. And that got immediate attention. And yeah, they didn't like that I found something, but they did understand the failure, which allowed them to actually execute a change, which was great. So that's all good. So I'm not sure. I'm going to leave it open to the chat window to answer a little bit more of Hoja. How do you deal with a designer that says, "Oh, your test was bad"? How do you prevent that discussion from happening? Yeah, it certainly does. Is get them involved and validate the process and what you're doing. Sean, I don't think using standardized tests is the answer. So many standardized tests, and I'm going to talk about standards next month in our webinar program. Sometimes they're actually not terribly useful. They're not really appropriate. Part of this is also, well, what decision does the designer need to make, or the program need to make, and how does this test provide that information, right? What are the stresses? What are the environments? What are the patterns of the testing we're doing? What kind of algorithms are we using to check if it's good or not, right? And part of it is, you're exactly right, Heike, I think it's pronounced, I'm sorry, is, what is the purpose of this test? What's the function for this? So many organizations have a suite of, say, environmental tests, and they run it on every product. And if you find a failure, we've passed the test, whatever that means, for years, and now all of a sudden we failed the test. Is that meaningful or not? Is it useful or not? Is there enough root cause analysis to understand why it failed? But more importantly, are we expecting failures? And that makes a difference in setting up the expectations for the program. Yeah, great ideas there. All good stuff. Yeah, perfect. All right, let me get rid of my drawing tool so it doesn't follow us along. But back to decisions. Every single test or experiment needs to have a connection to a decision. So, and I'm sure I've told this story before, and apologize for those that have heard it a few times, is the very first time I did an accelerated test, my boss walked into my office and said, here's a new product we're developing, and we need to understand, will it survive for 20 years with a relatively high percentage surviving for 20 years. I think it was 95% would survive 20 years. And this product was going to be encased in concrete in bridges in the northern Italy mountains of the Dolomites. And so I thought, oh, this is great. I get to go spend 20 years off in northern Italy checking the progress of this heating cable we were making. And he goes, no. We need to know the answer in 6 months. And this is a major decision between us and the customer to have evidence that this product will achieve the amount of functionality, the heat output, that's sufficient for its purpose, for what we're designing the product for and what they want to buy and use it for, when enclosed in concrete in a bridge for 20 years. And I'm like, oh, okay, so you need to know this in 6 months. And he goes, yeah. And so I had a constraint, 6 months. And the decision was, is this a viable product for its intended use? And I needed to provide enough information so that those decision makers could say, yes, this will work, or no, this is not likely to work. And then they could create a new product line or not. So By connecting that test to that decision, I had a timeline, I had criteria, how detailed the information needed to be, how rigorous the test and analysis need to be, and so on. But if I'm doing, say, a high temperature humidity test, who's going to use that information and for what purpose? Right? If I'm going to do a out-of-box test, it's a consumer product and we're going to get some people to unbox it and turn it on and see if it works. Who's going to use that information from that study? Right? Now, when we do functional testing in, say, a circuit assembly process, we're looking to see if the components are assembled correctly, if all the solder joints are there. And if they're not, the test should flag that part or that circuit board to get some repair or be discarded. And it's almost an automated decision process there. Yet by design, that's what we're trying to do there. Is this product assembled correctly? And that's fine. For a lot of the reliability work we do, it falls into a number of different categories or criteria, and we need to make sure that what we're doing is actually still connected to a decision. And let me spend a little more time on that here in a minute. Yeah, in test methods, Hojad, it's really good to specify what's the connection, what are we trying to do? Now, having talked a whole lot about testing, there's a bunch of stuff we do instead of testing, right? There's simulations and estimates and predictions and all kinds of other tools we use, the physics of failure models. We may use testing to validate those models and develop them. Yet at times, those are and develop them. And we don't even actually need to do testing. It's a whole lot more cost effective once you have those models and understanding in place. So it's to get to supporting these decisions that need to be made, we don't always have to do testing. It's not the only way to solve these problems. So just a quick thought there. Problems. Sorry, I wanted to plant there for you. So sometimes we run, we have even the simplest product can have so many different ways that we can test it, right? There's all kinds of cool stuff we can do. This little handheld product that had that battery wire problem before, it was a new product, a new industrial design, so to speak, and for a new application. And part of this early part of the process is we sat down and brainstormed, well, how many different ways can it fail in the customer's hands? And so it was like an FMEA, and we looked at all the different ways it could fail. And we ended up with like 40 or 50 different stresses or threats to this product failing. But some of them, we didn't know exactly how to test. How do you test a product to be robust, that if it's laying on the couch and somebody sits on it, that it doesn't fracture and create a sharp edge and cut somebody and cause injury? It was a safety concern we had. We knew it would be exposed to somebody sitting on it. And as silly as that sounds, it's a safety issue. And so we went about figuring out, how do you test that? It's a product on a soft surface with somebody's butt bone in just the right place. And is that enough to do a 3-point bend test, essentially? And we went off and measured those things. How about stepping on it? How much force does a human exert when stepping on something, when walking or jumping? Well, there's tables, there's books available that have a bunch of that information, and you can do a little bit of calculations. We went off and measured it. We went off and got a bunch of people to jump on some sensors, and we measured the amount of force they exerted with different kinds of shoes, different kinds of floor materials, and so on. And we created a little bit of evidence of how to go about testing this thing. But some of our testing is of all of those different ways we can evaluate and test something, right? We don't have time or resources to do them all. So one of the areas to focus on, what I recommend, are areas that have high risk. I call them the red flag areas. It's a new material, a new design, pretty much anything with new in the conversation. My ears perk up when I hear somebody say, oh, we're going to use this new facet or new feature of this polymer to do this XYZ thing. New. How much experience do we have with that, air quotes here, new thing? And part of that is we don't know what we don't know. And so we need to chip away at that area. And we need to characterize or understand those risks involved with the new things. The other part is areas that we know that we're stripping away margin, that because of the design criteria. Oh yeah, Mark, yeah, I just saw your note. Yeah, the slide download is right there. So I did put that in the in our regular display here for the presentation. But if you ask a series of your design teams of areas that have the least margin or the highest uncertainty, those are areas that you may want to make sure are covered in testing in one form or another. Are those areas of concern, that little element in the designer's back of their head going, you know, this part I'm not really sure about how it's going to work? Now keep in mind, in the prototyping and the design practices, we try to characterize the amount of variability that's going to occur. Yet, until we quantify that, it's really hard to know if that variability and the lack of margin results in a poor or failed performance. So those are a couple different areas that we want to go look at. Another one is that, let's say it's an iteration of a product and we're doing some improvements on it. Did we actually solve the problem that we set out to solve? Those are usually pretty common sense to go about doing. Another area to consider is that we have constraints. We have lots of constraints. I was working with one group that ran, I think it was on the order of like 35, 40 different specific tests on their, it was a server product during the development process. And the testing suite, once the design was considered locked down and close enough to being done, they would create a bunch of prototypes, and it would still take them about 6 to 8 weeks to run all of these various tests. And that was pretty expensive. Took a bunch of time on it. So George, we're on the slide that's labeled cost and time. It's got a little teacup on a stack of books. And so we're realizing that they were doing a bunch of testing, and what they did is their practice was is as they found an issue or they discovered something that happened in the field, they would add a test to their suite to make sure that they didn't have that issue ever again. And by and large, it was working for them. Their products kept getting better and better, but the burden of all the testing just continued to grow and was expensive. And in working with that team, many of the designers understood the test criteria and the issues they had in the past and how to design away from creating a failure with those specific criteria. And so what we did is we said, well, let's not do all 35 tests. Let's do the critical ones, the ones like on the last slide that we have the most uncertainty or risk associated with, areas that we know we need the information for to make a specific decision, to inform a specific decision. And then for the rest of these, let's do a random sample. We'll pick which tests we're going to run late in the program, so every designer knows that they could be physically tested. They also know that they need to design to avoid failures in those specific topics and issues. And so what happened is we did, instead of 35 tests, we did 10. And 5 of them were randomly selected. And it saved them hundreds and hundreds of thousands of dollars in every development process. But it maintained the the results they were getting, the continued decline in field failures. And so just having the criteria and a good understanding of what those criteria were and why they existed doesn't necessarily require testing. The team wasn't willing to just give up all the testings because it sends a message that we're not going to check. And so it goes back to that old adage which that program manager really lived by, is people do what you measure. And so the testing, even though it was random, what specific measures we did, they all had a finite chance of being measured. And so it created the right behavior within the team at a significant reduction in cost and time to make it happen. Now, in testing, there's all kinds of constraints. Some of us just can't get prototypes. Some of us don't have the time. Some of us don't have the equipment. Yeah, deal with it. If it's important for your organization to make the right decision, it's worth, and you need the information in order to make the right decision, and testing is the way to get that information, well, then you got to deal with the constraints you have and do the best you can. Understanding and communicating all of the risks that are associated with the trade-offs and the adjustments for the constraints you're dealing with. All right. If you only have, it was a sequence of tests that were done in an ongoing reliability test. And it was being done on this game controller for about 5 years. And every month, they basically requalified the product. Now, I don't typically run into data sets like that very often. I don't know why they tested everything that they tested as their end of development process every month. And it was hundreds of samples. And it costs, it was like $250,000 a month in testing costs between the protos and the test facilities and the analysis. And I was like, so I got all this data, I ran it all out, and I found the CPK values for many of the tolerances that were available were in the 20s and 30s. The process had been so dialed in, the design was so solid, that it would be more likely that somebody deliberately forced a failure to occur than the product actually failing in all of the variability of the process and materials they used. So we got rid of all but one test that actually was predictive of process changes that led to field failures. All the rest of them we got rid of. And the CPKs were unreal in vast majority of things. And so the first step was just plot the data, right? And then I started looking for tolerances and realized that the amount of variability that they were experiencing was so small for most of the things they were evaluating, it was ridiculous to even check. And so with a little data, we were able to convince them to save, millions of dollars a year. And it wasn't a hard sell, but I had to have the data. I was faced with creating a new ongoing reliability test, and my general process is, well, what are the things in our process that have the most risk to creating failed products in the field? Let's focus there. And they said, well, we do this all the time. We just do everything. And the unfortunate part is they didn't actually ever look at the data. So my first inclination when I heard that they don't actually use the information from these testing is, then why do it? If nobody's going to look, nobody cares about the information, why do it? And just stop doing that. It's kind of ridiculous. But I ended up getting that data and had fun showing them that there's really good reason to stop. A lot of their assembly processes and what they're already doing is very, very well done. So benefit from that and don't do testing just because. Tie your testing to the decisions your team needs to make. Now here's a question for you. Is every test of the same value or same use? No, right? Some tests are generic, benign, and They're a simple hurdle like powering on the prototype, right? And it has value. Hey, this first prototype works. We can go on with our development process. But others are critical, like that product I mentioned earlier for the bridges and the Dolomites. It was a major new application of our product in a new venue and opened up a whole new product line. That was tens of millions of dollars that rided on that test. And make a long story short, they actually did install those there. So if you're in the winter in the Dolomites, you'll notice that many of the bridges on the major roads are dry, even though there's snow and ice on the roads, which is the opposite of what we typically see. And that was that product I worked on so many years ago. All right. So there's all kinds of testing. Go through this pretty quick because I know you know about many of these. It's right. So we do out-of-box testing or shipping or installation-related stuff, right? Part of this we do because many of our failures occur early in the product's use. And some of it is the experience. Does the customer, it's like I just opened I bought a new computer from Apple. Their packaging is exquisite. It just fits well, it feels good, it's solid, it's elegant, it's minimal amount of packing material. As opposed to, I got some garden supplies from a greenhouse warehouse, I think it is. And it was a handmade box with some duct tape and parts of the product was hanging out of the outside of it. And I was surprised that actually the shipping label actually stayed on. It was so poorly done. Completely different experience, different market, obviously, but very different. But we do stuff like this because when you look at your field data, some proportion, often high proportion, of our failures occur early in the experience the customers have with our product. And as you know, those are very, very painful, especially if you're in the consumer world, right? If you're in the consumer world, it's that word of mouth and reviews that make a difference in how successful a product launch can be. And so making sure that the product arrives well or safe and functional and is easy to install are all critical aspects of the customer actually getting the benefit of the product they're buying. But I often get pushback on, is this a reliability issue? Well, many of you know my take on that is if it fails for a customer and it costs us money, right? A call, a return, or a lost future sale, it's a reliability issue. We need to deal with that. Now, these all can be solved by design, but if your testing is only at the end of life, you may be missing, say, a third to half of the potential failure mechanisms that really do cost you and your organization money. And so if it's not being done by somebody else, and in understanding the variability that occurs and the types of failures that occur and the magnitude or impact of those failures, it's something to add to your portfolio. It's something that we should do. We often do environmental testing or hazard or day in the life of type testing and so on. These are so common, and we ended up usually with so few samples that it's 3 samples at high temperature, and then we're going to run it at low temperature, and then we're going to vibrate it and to simulate a truck ride and pass. Well, if we had a 10% defect rate for high temperature products due to the variation of our system in its assembly, 3 samples are very, very unlikely to find a problem that only occurs in 1 in 10 of the products. So keep in mind what it is you're looking for, right? There are ways to, if the environmental stresses are important for your product and you need to know that it's working there, do enough evaluation such that you can detect the level of set of defects that are critical for you to make a decision. So if you need to redesign your product, if you have more than, say, 5% defect rate for some profile or use conditions or whatever, well, testing one sample is very, very likely to not find a problem, which is misleading when you're trying to find, are you exposed to a certain level of defects? So think that through. Will your test have the capability to find the defect level that is important for you to make a decision, right? And part of that is that discussion is, well, how bad is bad enough, right? If we're okay with the potential of 90% of our products being bad in some use condition, we don't need to do much testing then. It's pretty easy. But if it's critical for us to not have that risk, well, then you need to find the appropriate solution to get that information. Another part that more and more people are doing is looking for those areas that we did not expect to fail. So instead of just testing within the boundaries of proper use of your product, especially consumer products, is use it in ways that your customer would be deliberately abusing or misusing your product. It might say in the user's manual, don't leave on the dashboard of your car in Houston, Texas, and close up your car. It's likely to melt, actually. So, but they're going to do that, right? If that's a typical behavior, is to use your product in the car and it's handheld, and going for lunch as you leave it on the car seat or in the back window or in the sun, it probably needs to survive that experience, right? Moisture, Apple and others are making cell phones now that are moisture resistant. I don't know how moisture proof they are, but moisture resistant. After years and years and years of all of us having to be careful not to get our cell phones wet. And I'm sure as this new design sequence improves, people are going to say, hey, we want phones that survive drops, or we want phones that survive being sat on when it's in our back pocket, or survive transport in our purses and briefcases. Our expectations of our devices, is your customers' expectations of yours, will continue to evolve and change. And staying ahead of that is anticipating the unexpected. And so doing test of failure on all kinds of stresses, not just the common ones, but all kinds of uses and scenarios. This is the part I live for, is how can customers break our product? And does that create a safety hazard, or does that create a unwanted experience for them, or is it something that we're going to have to expect and deal with as we go? And what's the risk to our product and product brand perception? Now, discovery testing or discovery process. HALT, multiple overstress and multiple environment stress testing, I think is what it stands for. Margin testing. I think there's about a dozen other acronyms and names for this. Is a wonderful tool to learn about failure mechanisms. Now, let me pause there and say, do you always do one of these processes for every product you're designing? Is that something you always do? No, right? If you already have good information about how your customers are causing products to fail, you already have a Pareto of things to go solve. Let's go solve those, right? A HALT may or may not have a role there. If you're doing something new and novel in your design and you don't know how it fails, this is a perfect sequence of testing to do, or type of testing to do. Make sure each and every test is connected to a decision and adds value. So life, I mentioned that earlier. Now, when I think of life testing, it's often related to accelerated testing. We almost, some products don't aren't expected to last very long, so you can do real-time testing, right? That's great. But most of the time we're dealing with acceleration. But part of this is not, that's usually associated with specific failure mechanisms and a model and specific stresses and stuff. So it's pretty limited given all the ways your product can fail. We also start looking at things like durability and robustness. How resilient is your product to the wild world that's out there of how our products are used? How capable of it is to deal with the shocks and bumps and ups and downs of daily use? And how does it behave in those circumstances? So these are all types of tools that are often related to, is it good enough? Will it last 5 years with 98% surviving? Right? Those are types of questions we deal with these. So if you get a field failure, right, we often are trying to anticipate that. So organizations that have a really good reliability program, in my opinion, have anticipated how their product is going to fail and assess the magnitude of those, the chance of that failure and the impact of the consequence of that failure, and said, this is a trade-off. We can spend more time in the lab and try to solve that, or it's good enough. It's an acceptable failure rate. If the testing you're doing is not providing the information for you to anticipate your field failures, both magnitude and consequence, then I suggest that your failing is not all that good. So use this as a way to evaluate whether you're doing out-of-box testing or halt testing or life testing. Is it, or environmental testing, is it actually helping us to answer the question, which failures are we going to accept in our product going out to the field, and which ones are we not going to accept? And do we have enough information to know the difference, right? So on one extreme is you do a whole raft of testing, and they're all testing to pass, right? And so you pass, all these tests, there's no failures, and you still have field problems, right? Well, are you able to, and in some cases you are, were you able to anticipate and predict those specific failures that were occurring, and were those deliberately decided to be okay, acceptable for your current situation? Or did you do some really focused testing to get details on high-risk failure mechanisms such that, one, you had information to solve it, and two, you had information to decide, is this an acceptable risk of failure or not? Now, you can use that information even if you choose not to design it out of a product, or if you're technically not able to, is use that in your call centers and use it with your customers to help them understand the risks. I was working with a customer last week, and they were looking at IGBTs for an inverter application. And the way they were using it, one of the vendors that they were using had a white paper that showed the model for the number of cycles to failure for the particular stress the power cycling this component would see. And it helped them to understand their application, the effect of cooling, and the expected durability or the life of that particular component. But what they didn't know is how to interpret that into their design. And so just a quick couple of calculations and a simple model for their system, it became clear that they didn't need to go test this. They had the base information, but they needed it connected it to their overall system reliability goals, and we were able to do that. Now, if that vendor hadn't provided that level of detail about failure mechanisms, we would probably have to go test it, go find that information, create that model. And so when you can, use your existing information and avoid testing. It's usually way too costly. All right. So meaningful tests. They're timely, informative, and what else? Right? they make sense. We can connect it to failure mechanisms. We can estimate, project failures that are likely to occur in the field under different use conditions and so on. It's not too late, right? Or it just says pass or fail, or it just by design is unable to detect the defect rate that you're interested in, or to provide information that is useful for the designers or for the decision it's associated with. There's many other ways testing is just not useful. But I think you know what I'm talking about here. I mentioned a good number of them already. So the pin underneath all of this stuff I'm talking about is, for every test, for every experiment, what's the objective? Who needs to make what decision? And the acid test is, will the results of this test provide sufficient information to help them make a better decision? Right? That's the acid test. If the test has no failures, is that still useful? If all of them fail, is that still useful? If we get a mix of failures, again, is that useful? So think through the scenarios of what happens at the result of your testing. And under each of those scenarios, are the results still providing sufficient information to inform a decision? And now, bottom line, if there's no decision based on the results of your test, don't do the test. Save your time and money and use those prototypes and samples for something more useful. If it's a critical decision, it takes more work to get it right. If it's yeah, we need to do this, we have some risk here or some margin, make sure that your test evaluates the purpose of the decision. Right? Connect it every single time. There's no such thing as always running an 85-85 test. 85RH, 85C for 100 hours or 168 hours or whatever duration, and do it on every time you build a product. To me, that makes absolutely no sense whatsoever. So if you're doing that, stop it. Think through, what is that test going to tell you? And this is down to the chemistry and physics, right? What is the details of what it's doing to your product, and how does that inform the information that you need in order to make a decision? Is this product ready for shipment or not? That kind of thing. Yeah, so hopefully I'm stressing that well enough. So I won't have you answer this, but hopefully I gave you a few thoughts of how to improve your testing program and hopefully do less testing but more meaningful testing. And I think my final slide is a quick summary. What's the purpose? Are you addressing the risks? Are you within the constraints that you have set out in front of you? And it's a negotiation, right? If I want to achieve these kinds of information, I need to push on some of these constraints. But there's a cost-benefit trade-off here. Let's make sure we understand both sides of that and make sure they're focused on decisions. That's the bottom line. Okay, so I think the slides are still on the thing on here, so I'm going to pause here and see if there's any questions. I know I got lots of participation in the chat window. I really appreciate that. Let's see, I got a question here from Dale. Customer returns. No fault found. Now that's a good question. There's typically, anytime I look at field data, the number one Pareto item is no fault found. So before I do any testing, is take a look at how your product is diagnosed or repaired or returned. I've been in circumstances where the intent of the customer service team is to get the product repaired and back in service for the customer. Now these are usually repairable, more complicated products. It's turn it around quick. And if their standard practice is shotgun repairs, meaning they repair the 10 most common things that are likely to cause that symptom without diagnostic work, then 9 of those 10 circuit boards are going to be good. Or maybe all 10, it was just a connector that was a problem. So part of it is due to due diligence of what's the source of the returns products, and understand the propensity of getting no fault found. You may be getting a high percentage because that's your process. And is that acceptable financially and everything else to do? Does it make sense to go put a bunch of these products in a halt chamber to go force failures to occur, which is great for finding intermittents, latent defects, things that work fine at benign conditions or in your lab conditions, but don't work at the customer's conditions. If you fully suspect and can, know that this is a bad system or bad part back from the customer, but we can't make it fail here on our normal stuff, well, up your ante, up the stresses, and HALT is an excellent tool for doing that. But I hesitate recommending that only until you know what's the decisions that are leading to the stream of parts coming back to you. And if it includes deliberately returning good parts, then you've got other work to do and balances with the customer service team to understand that in a more detailed way. Maybe some screening before you get to failure analysis type work. So let's see, Williams got, let's see. So case, let's say I'm looking at, oh, I'm sorry, I'm not just at here. In that case, we really not understand the cause of failure then. Yeah. All of our testing, and most of our testing, I should say, not all of it, is really aimed at understanding failure mechanisms. That's what we can act on. Solving failure symptoms is usually a fruitless endeavor. We need to understand the root cause. So William's got a comment. A customer call, they call and give you a defined requirement, right? So they're playing a critical role in setting a requirement. And there's lots of industries that do that. That's no problem. Sometimes what they recommend is pretty useless. So it's a business decision. Do we do what they say and then keep going because we want to actually deliver a good product to them? Or do we abdicate and give them exactly what they asked for and hope for the best? Customers don't like failures, even if it's their fault. So it's a business decision. Where do we draw that line? And internally, are we there or not, right? So, how many units for a HALT program? I've heard all kinds of numbers. But basically, for, let's say, like a laptop, you're a product of that size and complexity and stresses that it's going to see, 2 to 4 is the common sequence I have. And usually you learn so much on the first one, you don't need to go after the second and third ones. If you're looking, there's not a, in my opinion, there's not a statistical significance there. It's if you've got access to lots of samples and can stress them in many different ways, then break up the tests and do them in parallel. Or do multiple stresses on a whole batch of things, especially if you're looking at process variation. The more samples is better. But if you're just looking at design robustness for a complicated product like a laptop or a similar device, then 2 samples is great, and many times 1 is enough in order to find lots of good stuff. Good questions. Good questions. So now, next month, before I forget, I'm going to talk about reliability-related standards, the good and the bad and the ugly of those. And this was a recommendation a couple months ago from one of the participants on a topic they were interested in. So I want to just shout out, say thanks for the suggestion. It's actually a pretty good topic. The more I dug into it, the more I think an hour is going to be tight to cover.